The system we're considering in this lecture is the quantum harmonic oscillator. There are a few ways to solve the Schrodinger equation for the quantum harmonic oscillator, but what we're going to do in this lecture is a solution more or less by pure cleverness. The solution is called the solution by ladder operators, and we'll see what that means in a few minutes. Just to set the stage, the potential that we're working with here is the potential of a harmonic oscillator. The amount of energy, essentially, that you get if you displace a particle attached to a spring from equilibrium. If you remember spring potential energy, the potential as a function of x is 1/2 the spring constant times the displacement x squared. But it's traditional to write this instead in terms of the angular frequency. The angular frequency of the oscillations that result when a mass m is on a spring with spring constant k is the square root of the spring constant divided by the mass of the particle. And if you substitute this in here and mess around with the simplification a little bit, you end up with 1/2 m omega squared x squared. So this is the form of the potential that we'll be using. What this looks like, if I plot it, is a parabola. Not the world's prettiest parabola, but you get the idea. And we know a little bit about what solutions to the Schrodinger equation should look like under circumstances like this. Let me draw this a little lower so I have room. If I have some energy E in this combined energy wave function axis, making a diagram of what the wave function looks like, if I start my wave function here, you know in this region the energy is above the potential, so the Schrodinger equation solutions have to curve downwards. And what they end up looking like is, well, something like this, say. Now in the regions outside here, where the potential is above the energy, the Schrodinger equation solutions curve upwards. In the case of the harmonic oscillator solutions, they curve just down to kiss the axis. And you end up with a nice sort of hump-shaped wave function. If you have a higher energy, say up here, it's entirely possible to get solutions that look different. Suppose I started my wave function here, pointed at some angle. The energy now is higher relative to the potential, so the wave function is going to curve more, and it's possible to make it curve down to the point where when it reaches this point now where the potential is higher than the energy and it starts curving back upward, you again get a wave function that just smoothly joins in with the axis, giving you a sort of nice normalizable wave function. So these are the sorts of solutions that we expect to get. If you want to get these solutions just by, well, like drawing them, like I just did, you can conceptually understand what they look like, but quantitatively you'll have to do a lot of fine-tuning to get these energy levels exactly right and to get the initial conditions here. I just started my wave function. How high up should I start my wave function? Or in this case, should I start it at the middle? Should I displace it? What should this angle here be? Fine-tuning like that is hard, and we'll see how to do that in the next lecture. But in this case, we're going to make a solution by cleverness instead of fine-tuning. To set that up, let's go back to the time-independent Schrodinger equation. This is the general time-independent Schrodinger equation, where now we're going to be substituting in the harmonic oscillator potential, 1/2 m omega squared x squared. That means the harmonic oscillator time-independent Schrodinger equation that we actually have to work with minus h bar squared over 2m times partial derivative of psi with respect to x squared plus 1/2 m omega squared x squared psi is equal to E psi. So this here is the Hamiltonian operator. The time-independent Schrodinger equation is also often just written as h psi equals E psi, and that's fine. Let's take a closer look at this Hamiltonian operator. Maybe we can do something with it. The cleverness comes in this step. Consider factoring the Hamiltonian. Well, I can simplify this a little bit by pulling out, for instance, a 2m here, and writing this as the momentum operator squared. This is essentially p squared over 2m, the kinetic energy part. This is the potential energy part. If I pull out an over 2m, what I get, 1 over 2m p hat squared plus m omega x quantity squared. This is suggestive. If we had numbers, and I had something like a squared plus b squared, I could factor that over the complex numbers as ia plus b times minus ia plus b. If you expand this out, you'll end up getting a plus a squared from multiplying these, a plus b from multiplying these, and similar to the cross terms in, say, a minus b times a plus b, the cross terms end up canceling out, and we would end up with what we started. Now, this is suggestive. You can't actually factor operators like this because they're not numbers, they're operators, and operators don't necessarily behave the same way numbers behave. We'll see what that means in a minute, but for now, let's just suggest looking at things like this. Plus or minus I times the momentum operator plus m omega x, where x now is the position operator. Now x, the position operator, just entails multiplying by x, so perhaps I should put a hat here, perhaps I shouldn't. Doesn't really matter. This is what we're considering now. I haven't justified this in any way beyond saying it kind of looks like maybe it would factor. Well, does it factor? These things are called ladder operators, and they're traditionally defined, just to make the notation a little bit simpler, a hat, and there's either a plus or a minus on this. Let me draw this a little bigger. A hat, plus or minus in the subscript, and these are defined to be 1 over the square root of 2 h bar m omega. The constant just makes things more nice overall, times minus or plus I p hat plus m omega x. This is now the position operator x hat. So this is the traditional definition. Let's see. If we have something that properly factors, what we should have is that a hat minus times a hat plus is our Hamiltonian. Is this true? This is an operator algebra problem, and operator algebra problems are tricky to do without test functions, but initially we can just write this out. We have two a's being multiplied together, so we're going to have a 1 over 2 h bar m omega out front, and then we're going to have I p hat plus m omega x times minus I p hat plus m omega x. Once again, hats on the x's if you prefer. So far, we've just written down our operators in order. Now, if I actually tried to expand these out, 1 over 2 h bar m omega. Now, this term, I times minus I, that's just plus 1. So we would get p hat squared. So far, so good. For this term, this is okay as well, plus m squared omega squared x hat squared. That's still okay. We're still on track. This was more or less what our Hamiltonian looked like. The cross terms get a little more interesting, though. We have a term like this, which gives us, let's see, we're going to end up with a minus I from this, minus I m omega, and we have x hat p hat. We're going to end up with something very similar from this term. We're going to have an I, we're going to have an m, we're going to have an omega, except in this case we're going to have p hat x hat, not x hat p hat, as we had here. So I'm going to factor the constants out and do that in the right color. That means we're going to have minus p hat x hat here. So this is what we get when we expand this out. This part here looks a lot like the Hamiltonian. So we're on the right track. It's actually like 1 over h bar omega times the Hamiltonian. This part, though, this is a little more difficult to work with. And it turns out that this piece right here, this sort of thing appears a lot in quantum mechanics, and we have a name for it and a notation for it. And the notation is x hat comma p hat in square brackets. This is called a commutator. And fundamentally, the fact that I can't just subtract these two things from each other and get zero is one of the most fundamental parts of quantum mechanics, one of the most fundamental features of quantum mechanics. So, let's talk about commutators in a little more detail. The commutator in general is defined for two operators A and B to be what you just saw on the last page. First, I have A, B, and then I subtract the opposite order, B, A. So if I acted on this, or if I used this operator, this combined operator, to act on a wave function, I would first let A act and then let B act. And I would subtract that from what I get if I let B act and then A act. Just to make that a little more explicit, if I had A, B minus B, A acting on some wave function, I would say that's A, B, psi minus B, A, psi. You don't necessarily get the same answer for both of these things because the order in which operators act is important. So let's look then at our commutator. The commutator we had in the last slide was x and p. The commutator of x and p is x hat, p hat minus p hat, x hat. And let's allow this to act on some wave function psi. In order to make my notation correct, I ought to have the same sort of psi here. So if I allow this to act on psi, first we're going to have x hat p hat psi minus p hat x hat psi. And what this means is x hat is acting on p hat acting on psi, and this is p hat acting on x hat acting on psi. We have definitions for these things. X hat is just x multiplied by something, and p hat is minus I h bar times the derivative of something, in this case psi. Our second term here is minus I h bar times the derivative of, with respect to x, of x times psi. When I apply the derivative here, I have to use the product rule since I have a product of two terms. I'll have to hit x in one term and psi in the other term. So, on the leftmost term here is easy to deal with, though. It's just minus I h bar x d psi dx. Actually, let's factor out a minus h bar, I h bar, from both terms, since they both have it. So x d psi dx is my first term here. Then I have minus, if I use the derivative on the x, derivative of x with respect to x is just 1. So all I'll be left with is the psi remaining untouched in the product rule. And if I let the derivative hit the psi, I'll leave the x untouched, and I'll have the derivative of psi with respect to x. This is good because here I have an x d psi dx minus x d psi dx. So I can let these terms subtract out and cancel. And what I'm left with, I have a minus I h bar times minus psi, which is just going to be I h bar psi. So I started with the commutator acting on the wave function, and I just got constant multiplied by the wave function. So I can drop my hypothetical wave function now and just write an equation involving the operators again. The commutator of x and p is I h bar. It's a weird looking equation, but you can see, if you recall from the last slide, what we're going to end up with. When we evaluated a minus hat, a plus hat, we ended up with 1 over h bar omega times the Hamiltonian, plus some constants. and if you flip back a slide, the IH bars end up actually canceling out, and we just end up with plus a half for our constant. So while we did not succeed in fully factoring the Hamiltonian, we did get the Hamiltonian back plus a constant. And if you reverse the order and repeat the algebra, a hat plus a hat minus, you end up with the same sort of thing. It looks very similar. You get 1 over h bar omega times the Hamiltonian minus a half instead. What this means is we can express the Hamiltonian in terms of these ladder operators and these constants. What we get for the Hamiltonian, h hat, is h bar omega times a minus a plus operators minus a half. Or alternatively, the Hamiltonian is equal to h bar omega a plus a minus plus a half. So these are the sorts of things that we got from our operator algebra after attempting to factor the Hamiltonian. That was pretty clever, but it didn't actually get us a solution. It just got us a different expression of the problem. The cleverness really comes in considering ladder operators and energy. The time-independent Schrodinger equation here is h hat psi equals E psi. So suppose we have some solution psi to the Schrodinger equation. We can then express the Hamiltonian in terms of these ladder operators, h bar omega times a plus a minus operators plus 1/2 acting on the wave function should be equal to E times the wave function. The clever part is this. What if I consider h hat times a plus psi? What happens to the wave function if I allow a plus to act on it before I allow the Hamiltonian to act on it? Now, assuming this is the case, maybe we can manipulate our expressions here involving the Hamiltonian and the ladder operators to get something with which we can apply our solution. Let's see what happens. Expressing the Hamiltonian now as ladder operators, h bar omega a hat plus a hat minus plus 1/2, now acting on a plus hat psi. Forgot my hat there, sorry. Looking at this, you can take a plus psi and distribute it in to the expression in parentheses here. H bar omega a plus hat a minus hat a plus hat psi plus 1/2 psi. Put another way, I'm really just distributing the operator in. And that's actually a more convenient way to look at it. So I'm going to erase my psi's here, and I'm going to leave my psi outside the expression. Oops, and I forgot an a plus hat here. Sorry about that. Just distributing the a plus in here, you'll end up with plus minus plus, and just plus on the 1/2. Now, you notice I have an a plus here, and an a plus here. If you think about factoring this out to the left, that's actually allowed as well. I can rewrite this as h bar omega a plus hat in front of the expression a minus hat a plus hat plus 1/2, all acting on psi. That's okay. What's nice about this is if you look, we have here now an h bar omega and an a minus a plus. If I had the appropriate constant here, which would turn out to be minus 1/2, I would have the Hamiltonian back. And getting the Hamiltonian back means we might be able to apply our Schrodinger equation. So let's rewrite this as h bar omega a plus hat times a minus a plus minus 1/2 plus 1. I haven't changed anything now, except this piece. This is my Hamiltonian. I had two expressions for the Hamiltonian that I got from calculating the product of ladder operators. One if I did a plus first and then a minus, one if I did a minus first and then a plus, and they were different by the sign that appeared here. So the fact that this is the Hamiltonian allows me to rewrite things a little bit. It turns out I can rewrite this whole expression as a plus hat acting on the Hamiltonian, and you have to distribute the h bar omega in, Hamiltonian operator plus h bar omega acting on psi. So I'm starting to lose my ladder operators, which is a good sign because I don't actually want expressions with lots of ladder operators in them. I'd like expressions with things that I know in them. And it turns out you know what happens when the Hamiltonian acts on psi. So if I distribute psi in here, I'll just have psi times h bar omega and the Hamiltonian acting on psi. But you know the Hamiltonian acting on psi is E times psi. So we're definitely making progress now. This is going to become a plus hat times E plus h bar omega psi. This now is all constant. So it doesn't matter if I put it in between the ladder operator and the wave function or not. So I can pull that out and make this E plus h bar omega times ladder operator a plus acting on the wave function psi. If I rewrite my entire equation then, I end up with h hat acting on ladder operator psi, a plus psi, is equal to E plus h bar omega ladder operator acting on psi, a plus acting on psi. This looks a lot like the Schrodinger equation for a wave function given by a plus psi. So, if psi is a solution to the time-independent Schrodinger equation, a plus psi is also a solution to the time-independent Schrodinger equation with this new energy. That's really the clever part. If psi is a solution, a plus psi is also a solution. That's really quite interesting. What that means is if I have one solution psi, I can apply the ladder operator, which I've just been writing as a plus hat here, but we know what the ladder operator a plus is. It's a combination of the momentum operator and multiplication by x with appropriate constants thrown in. We know about a plus psi. If we knew the wave function, we could actually do this. It would involve taking some derivatives and multiplying by some constants. We can do that. So this gives us some machinery for constructing solutions from other existing solutions. We haven't actually solved the system yet. There's a little bit of cleverness left. And this has to do with ladder operators and the ground state. What we showed on the last slide was that if psi was a solution, then a plus hat psi was a solution with energy E plus h bar omega. It turns out a minus hat psi, you can follow through the same algebra, is also a solution, but it has energy E minus h bar omega. So suppose we have some solution, psi, and I'll call it psi sub n now. If we apply the ladder operator, a plus psi, we'll end up with some wave function psi n plus 1. It's another solution to the Schrodinger equation. It has a slightly higher energy. The energy has been increased by the amount h bar omega here. I can repeat that process, and I'll get, say, something I would call psi n plus 2. And you can keep applying the ladder operator over and over and over, and you'll generate an infinite number of solutions with higher and higher and higher energies. We can also apply the ladder operator a minus hat, and you'll get something I'll call psi sub n minus 1 with slightly lower energy. The energy has been lowered by an amount h bar omega. You can apply the ladder operator a minus hat as many times as you want, of course, as well, and you'll get psi sub n minus 2, or psi sub n minus 3, or psi sub n minus 4, or psi sub n minus 5. Every time you apply the lowering operator, the ladder operator a minus hat, you get another solution with lower and lower and lower energy. But we know if we have a wave function with very, very low energy, it's going to behave very strangely. If your potential, for instance, is your harmonic oscillator potential, it looks like this, and your energy, E, is below your potential V of x, then if I start my wave function, say, anywhere, really, let's start it here. The fact that the energy is below the potential for the entire domain of the potential means that over the entire domain of the wave function is going to be curving away from the axis. The wave function is going to be blowing up. That's a problem. I cannot have solutions with arbitrarily low energy. What that means, cannot have solutions with very low energy. What that means is that if I apply this lowering operator over and over and over again, sooner or later I have to get something that I can no longer apply the lowering operator to. Something will no longer give me a meaningful solution. And it turns out the best way of thinking about that is there is some wave function such that A minus acting on that wave function is equal to 0. If we have a state like this, this will be our lowest energy state, and I'll call it psi sub 0. This is a necessary condition for getting a normalizable wave function. If we did not have this condition, we'd be able to keep applying the lowering operator, and we would sooner or later get solutions that were not allowed. That's a problem. So let's figure out what this actually implies. We know what the lowering operator is. We know what 0 is. We ought to be able to solve this. This is going to be an ordinary differential equation just given by the definition of the ladder operator. 1 over 2m h bar omega in the square root times the momentum operator h bar d by dx plus m omega x acting on psi sub 0 is equal to 0. This we can solve. This is a relatively easy ordinary differential equation to solve, in fact, because it's actually separable. If you mess around with the constants, you can convert this into the differential equation d psi dx is equal to minus m omega over h bar x psi. And these are now psi zeros, sorry. This can be directly integrated. I can rewrite this as d psi over psi is equal to minus m omega over h bar x dx. And if I do this integral, integrating both sides of this equation, what you end up with, after you simplify, is that psi sub 0 is equal to e to the minus m omega over 2 h bar x squared. E to the minus x squared for our ground state, for our lowest energy psi sub 0, for our lowest energy solution. There's a normalization constant here, and I'll save you the trouble of calculating the normalization constant out. It's m omega over pi h bar to the 1/4 power. So this is our ground state. Now it's off to the races. By consideration of the Hamiltonian, and attempting to factor it, and defining ladder operators, and exploring the consequences of these ladder operators, in particular that we ended up with any single solution giving us an infinite number of solutions by repeatedly applying a plus and a minus, the necessity of a normalizable wave function, the necessity of having a lowest energy state, meant that we got an equation that was simple enough that we could solve it with just simple ordinary differential equations. Now, there's really no such thing as a simple ordinary differential equation, but this was a lot easier to solve than some ordinary differential equations. What that ended up giving us in the end was psi 0, our lowest energy state. We can then apply the raising operator, a plus, over and over and over again to construct an infinite number of states. To summarize, here's a slide with all of the definitions. The raising and lowering operators, the ladder operators, a plus and a minus, the expressions that you get from simplifying the Hamiltonian in terms of the ladder operators. I want to highlight these two expressions because I have not completely derived them. I have argued that the ladder operator a plus applied to some wave function psi sub n gives you psi sub n plus 1, but I haven't told you anything about the normalization. You could apply this operator over and over again and renormalize all of the wave functions you get as a result, but it turns out there's a pattern to them, and that pattern is that what you get by applying the ladder operator a plus to psi n is not psi n plus 1, but psi n plus 1 times this square root of n plus 1. Likewise for the lowering operator. There's a nice explanation in the textbook of how you can use still more cleverness to derive what these normalization multiplicative factors are. Our ground state we got from applying the lowering operator to some hypothetical wave function, which when we solve it, we ended up with this, our psi sub 0, our lowest energy wave function. Putting all of this together, you can come up with an expression for the nth wave function, psi sub n, in terms of psi sub 0. You have to apply a plus n times. This superscript n here means to apply a plus n times. For instance, a plus hat cubed would be a plus, a plus, a plus, all acting on, say, if there's a psi in here, all acting on the psi, just one after the other. And if you calculate the energies that we get, applying the Hamiltonian to our lowest energy wave function, and then knowing that raising the operator a plus gives you a new solution with an energy that's increased by the amount h bar omega, you end up with the energies. So we actually know everything about the solutions now. We know the lowest energy solution, we have a procedure for calculating higher energy solutions, and we know the energies of all of these solutions. So that's wonderfully good. To give an example of how these things are actually used, let's calculate psi 1. We know psi 1, buying black a little easier to read, psi 1 is going to be equal to a plus acting on psi 0, and there's that normalization constant, the square root of n plus 1, except in this case n is 0, so this is just going to be 1. If I substitute in the definition of the operator a plus, that's 1 over that square root of 2 h bar m omega minus I p hat plus m omega x, where p hat now is minus I h bar d by dx. This is my raising operator. That's all acting on psi sub 0. And we know psi sub 0, given in normalized form, m omega over pi h bar to the 1/4 power e to the minus m omega over 2 h bar x squared. We just have to evaluate this, taking derivatives of this exponential and multiplying it by x. So let's continue with that. Moving our normalization constant out front, m omega over pi h bar to the 1/4 power over this square root factor, 2 h bar m omega. Simplifying this expression out, we end up with minus h bar d by dx plus m omega x, all acting on e to the minus m omega over 2 h bar x squared. Now, this term with the m omega x, that's going to be easy. The derivative here is going to be relatively straightforward as well. And what we end up with is the constants we had out front, and taking the derivative of an exponential, we're just going to get the exponential back. So we're going to have an h bar e to the minus m omega over 2 h bar x squared times the inner derivative, the derivative of what's in the exponent itself, which is minus 2 x, sorry, let me actually write this out, minus m omega over 2 h bar times 2x. That's okay. The minus sign here and the minus sign I had out front will end up canceling out. I can simplify, I can cancel out my 2's, I can cancel out an h bar. That's all I'm going to do with that term for now. The other term is easy. m omega x e to the minus m omega over 2 h bar x squared. So that's our result. We have an e to the m minus m omega, etc., over x squared in both of these terms. So I'm going to pull that out to the right. And if I pull my constants out to the left, I have an m omega and an m omega in both of these terms, so I can factor that out. And what you end up with at the end, after all is said and done, the only step I'm skipping now is to simplify the constants. What you end up with is m omega over pi h bar to the 1/4 power. There isn't much we can do about that. Square root of 2 m omega over h bar x e to the minus m omega over 2 h bar x squared. Both of these terms had x and x in them. So these terms just add up, and this is what we end up with at the end. This is your expression for psi 1. The algebra here gets a little bit complicated, but fundamentally what we're doing is calculus, taking derivatives, multiplying, manipulating functions, applying the chain rule, and turning the crank, more or less. The formula we started with here does give us machinery that we can use to calculate any wave function that we might want as a solution to the time-independent Schrodinger equation for the quantum harmonic oscillator. To check your understanding, here is an operator algebra problem. Given that x hat is the position operator and t hat is the kinetic energy operator, essentially p squared over 2m, calculate the commutator of x and t. Now it's just defined as this. The one tip I have for you here is to be sure to include a test function when you expand out these terms, and when you take second derivatives, do it as a sequence of 2 steps. Don't just try and take the second derivative twice in one step. You may have to apply the product rule. The system we're considering in this lecture is the quantum harmonic oscillator. There are a few ways to solve the Schrodinger equation for the quantum harmonic oscillator, but what we're going to do in this lecture is a solution more or less by pure cleverness. The solution is called the solution by ladder operators, and we'll see what that means in a few minutes. Just to set the stage, the potential that we're working with here is the potential of a harmonic oscillator. The amount of energy, essentially, that you get if you displace a particle attached to a spring from equilibrium. If you remember spring potential energy, the potential as a function of x is 1/2 the spring constant times the displacement x squared. But it's traditional to write this instead in terms of the angular frequency. The angular frequency of the oscillations that result when a mass m is on a spring with spring constant k is the square root of the spring constant divided by the mass of the particle. And if you substitute this in here and mess around with the simplification a little bit, you end up with 1/2 m omega squared x squared. So this is the form of the potential that we'll be using. What this looks like, if I plot it, is a parabola. Not the world's prettiest parabola, but you get the idea. And we know a little bit about what solutions to the Schrodinger equation should look like under the axis. And you end up with a nice sort of hump-shaped wave function. If you have a higher energy, say up here, it's entirely possible to get solutions that look different. Suppose I started my wave function here, pointed at some angle. The energy now is higher relative to the potential, so the wave function is going to curve more, and it's possible to make it curve down to the point where when it reaches this point now where the potential is higher than the energy and it starts curving back upward, you again get a wave function that just smoothly joins in with the axis, giving you a sort of nice normalizable wave function. So these are the sorts of solutions that we expect in circumstances like this. Let me draw this a little lower so I have room. If I have some energy E in this combined energy wave function axis, making a diagram of what the wave function looks like, if I start my wave function here, you know in this region the energy is above the potential, so the Schrodinger equation solutions have to curve downwards. And what they end up looking like is, well, something like this, say. Now, in the regions outside here, where the potential is above the energy, the Schrodinger equation solutions curve upwards. In the case of the harmonic oscillator solutions, they curve just down to case to get. If you want to get these solutions just by, well, like drawing them, like I just did, you can conceptually understand what they look like, but quantitatively you'll have to do a lot of fine-tuning to get these energy levels exactly right and to get the initial conditions here. I just started my wave function. How high up should I start my wave function? Or in this case, should I start it at the middle? Should I displace it? What should this angle here be? Fine-tuning like that is hard, and we'll see how to do that in the next lecture. But in this case, we're going to make a solution by cleverness instead of fine-tuning. To set that up, let's go back to the time-independent Schrodinger equation. This is the general time-independent Schrodinger equation, where now we're going to be substituting